Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on December 29, 2025, about 2 days ago. This paper shows that end-to-end test time training can match full attention scaling with long context while keeping constant inference latency, reaching about 2.7 times faster than full attention at 128K context. The paper is titled End-to-End Test Time Training for Long Context. And as we'll see later, the idea of compressing long context into the model's weights leads to some surprisingly strong results. Also, the authors shared an official JAX codebase on GitHub. You will find the training and test time training implementation, Hydra configs to reproduce the paper's experiments, and setup notes for GPUs and dependencies. The repo also includes dataset download instructions, weights and biases logging hooks, and Slurm submit launch scripts for multi-node runs. Figure 1 makes the core claim concrete, because it shows you can keep long context quality while avoiding full attention slowdown. The full figure area is the two side-by-side plots at the top. The left plot reports loss delta, meaning extra loss relative to full attention, and the blue TTTE2E line stays best as context reaches 128K. The right plot shows pre-fill latency, where blue stays nearly flat while orange rises sharply. Figure 2 gives an intuition for how test time training creates memory by updating weights on the context itself. The full figure contains a left diagram and a right plot. On the left, the model predicts a token, computes next token loss, and takes a gradient step, so the blue updated multi-layer perceptron blocks store information from prior tokens. On the right, the end-to-end version with mini batch size 1 tracks close to full attention loss, while naive test time training lags. Table 1 shows that swapping key-value binding style losses for a single end-to-end next token loss gives a small but consistent quality gain. The full table compares methods by language modeling loss, which is lower when predictions are better. The sliding window attention baseline sits at 2.83. The bottom rows show the end-to-end variant reaching 2.81, so the change in objective matters more than minor simplifications. Figure 4 pins down which knobs actually matter for end-to-end test time training performance. This figure contains 3 plots across the top that summarize the ablations. The left panel shows that larger sliding window size improves loss for all methods, so the authors settle on 8K. The middle panel shows that larger test time training mini batch size slightly hurts loss, which supports using 1K. The right panel shows that updating more layers helps at long context, because updating only one layer drifts toward worse loss delta. Table 2 shows that when the task demands exact recall, full attention wins by a lot, especially as context gets longer. Needle in a haystack means the model must retrieve a specific out-of-place string from a long passage, so near lossless memory matters. In the SNIAH1 block, full attention stays near 1 while sliding window attention drops sharply at longer context. The TTTE2E row improves over some baselines, but still falls short on these recall-heavy tests. Alright, 2 takeaways stand out. First, end-to-end test time training lets a sliding window attention transformer keep improving as context grows, while inference latency stays constant, which makes very long context use much more practical. Second, the trade-off is that exact recall still favors full attention, so memory quality is not fully solved yet. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.